Hello everyone, I am Dr. Rijit Kumar Dre from IISER Mohali. So this time I am offering a course on advanced chemical thermodynamics and kinetics. So prior to this course, I also offered another course on introductory level chemical kinetics and thermodynamics. So a general introduction or general knowledge about the introductory level thermodynamics and chemical kinetics will be required for this course. But you can always go back and look at my earlier course to get an idea. So in this advanced course, we'll be covering a few topics. We'll start with a review of classical thermodynamics, which we covered in the earlier course. So we'll give you a concept of entropy, the properties of Gibbs and Helmholtz free energies, and a little bit concept of the phase equilibrium. We'll also talk about chemical equilibrium or thermodynamics of mixtures and little aspects of chemical equilibrium. And then we'll move on and we'll first discuss about molecular interactions. And this is very important because due to molecular interactions or intermolecular interactions, we have condensed phases like gas forms liquids and liquids form solids. So we'll just try to understand what is the underlying mechanism of this. We'll be first talking about moments of forces like dipole moment, and then we'll talk about electrical polarization and different types of interactions like between charge and a dipole or a dipole and so on. And we'll also talk about the repulsive interaction, how the total interaction scales with distance. And then we'll be talking about the transport phenomena, where we'll be covering mostly viscosity and diffusion. And these two are very, very important because we'll be giving you a lab demonstration on viscosity later, and we'll be using the concept of diffusion in describing chemical reaction dynamics in solution afterwards. Next thing we'll cover is we'll give you a review of chemical kinetics. Now again, we'll just go through the basic concepts like reaction mechanism and what is known as kinetic measurements. Next, we'll go to the advanced topics in chemical kinetics, and there we'll be talking about photochemistry. We'll give again a very introductory level discussion on the Jablonski diagram. And then we'll also talk about kinetics of multi-component systems, where we'll talk about combustion as well as atmospheric reactions. Next, we'll be talking about statistical thermodynamics. Again, I will be giving you a very brief introduction, which will be required to understand chemical reaction dynamics, particularly the statistical theories of reaction dynamics. And there we'll be only talking about the molecular partition function, how the Boltzmann distribution arises, and how we can successfully use the Boltzmann distribution to calculate partition functions with respect to various motions of the molecules or degrees of freedom of the molecules. And next we'll be introducing you to the concept of reaction dynamics, where we'll be talking about the potential energy surface. In the earlier course, we also had a topic on reaction dynamics, where actually we gave introductory concept on collision theory. So we'll try to make an analogy or a connection of that model, which is based on collisions between molecules and the potential energy surface. And there we'll be talking mostly about the transition state theory. And in the next topic, we'll be talking about the unimolecular reaction, how basically a bimolecular reaction precedes the unimolecular reaction, and once we have an energized molecule, how statistical theories can help us to predict the rate constant or get an expression for the rate constant. Again, this is a very involved topic and we cannot go through the detail. So we'll give you an overview of the theories which are known as the Rives, Ramsperger and Castle model, or the RRK model, and the RRKM model, which was modified by Rudy Marcus. And then we'll be moving to the more advanced topics, which are introduction, giving you an introduction to the condensed phase reaction dynamics. And there we'll be first talking about what is the cage effect in reaction. And then we'll be talking about the diffusion control reaction. We'll talk about two particular topics where we'll show you how solvation plays a very, very crucial role in controlling or influencing the rates of the chemical reaction. One is basically electron transfer reaction, and we'll be talking about the Marcus model of electron transfer. And the second one is polar solvation dynamics. Next, we'll be talking about ions. Now, this chapter is actually consisting of many different topics which can be connected to earlier chapters. For example, this activity of ions, where we will be talking about the de-bivehicle theory, is connected to the thermodynamics part, where we talked about the existence of the concept or the concept of activity, how it emerges for non-ideal systems, how actually people introduce the concept of activity to describe the departure from ideality or ideal behavior. We will also talk about colloids, because colloids are charged particles. We will be talking about the stability of the colloids again very briefly, and we will also talk about ionic conductivity. Now, this ionic conductivity part can be read with transport phenomena, and then we will also talk about reactions between ions, which can be actually read with the chemical kinetics part. And then we will be showing you a very interesting thing, where actually we will show you some real life experiments, where we will give you some demonstration of the four very interesting experiments. Where the first thing we will show you, took a topic from the transport phenomena, where we will show you how one can measure the coefficient of viscosity. And then we will be talking about experiment in chemical kinetics, where we will show you how one can measure the rate constant for hydrolysis of esters. Next, we will be talking about the degradation of a dye, how one can find the photochemical degradation and the kinetics associated with it. And last thing, we will show you a very advanced laser lab. We will give you a virtual tour, and we will show you how one does a femtosecond pump probe spectroscopy to understand the kinetics or the dynamics with femtosecond accuracy. Remember that 1 femtosecond is 10 to the power minus 15 seconds or so, which is basically 1 divided by 1 followed by 15 zeros. So that much time accuracy we need to understand chemical reaction dynamics, and in modern times we have those kind of facilities. And we will conclude this lecture, we will conclude this course with a concluding remarks where we will be talking about the summary and the future outlook of this course. So I hope you will enjoy this course. Thank you very much.